Let's take a look at finding z-scores. Z-scores are a method of standardization for variables. Many different variables that are normally distributed, from weights at birth of babies to test scores to IQ scores. However, they are all measured on different scales. For example, your IQ score is not measured on the same scale as your weight when you're born. So we use a z-score as a way to analyze these scores. This allows us to have one standard variable for comparison purposes. Okay? So we can use this to compare all kinds of things depending on the mean and standard deviation, and it's all about the relationship to standard deviation. So we use this formula where we take our x value, and I put an n there to indicate we can give this a number, the first x value, the second. For example, in my class I might give you the values 1 through 25 and find your z-score for a particular assignment. We subtract the mean and divide by the standard deviation. This tells us, it gives us a relative position, mean and standard deviation. So for this particular distribution, the mean will be equal to 10 and standard deviation equal. We want to find Z1 who scored an 8. Now the 8 goes in the X spot. We can go ahead and let's erase this circle so we can see that this is the X score right here. The X score, the individual student score, or individual person score, is 8. We subtract the mean and divide by the standard deviation. Now recall that the mean in this case is 10, so that goes where that funny looking M, the Greek letter mu, goes. The standard deviation is 3, so that goes in that part of the formula. And the only thing we're going to alter is the individual's score, the xn. So I'll go ahead and subtract 8 minus 10 is negative 2 and divide that by 3. And get a z-score for this particular student of 0.067. It is a very common thing to round our z-scores to 2 decimal places. And that gives me a comparison for that student in terms of how many standard deviations they are below the mean, and a comparison to the mean and the standard deviation. Now what if we had another data point, 12? We could find that individual's data point by using the same formula. Now notice the mean and standard deviation do not change. It's only the x value. So x2 is 12, so that x value changes to 12. The mean stays the same, and the standard deviation stays the same. Upon doing the math, 12 minus 10 is 2. 2 divided by 3 is I'm going to run out of room, gosh dang, a positive 0.67. Okay? So we have our z-scores for the two individual students. It shows, or people, or whatever they are, it shows their relative score to the mean and standard deviation. The last thing we need to know is that if the area between the two of these on the normal curve is 0.495, what is the area between Z1 and Z2? So if we had a specific normal curve we could draw for this specific case where the mean is 10 and the standard deviation is 3, so it would go something like this. Mean goes in the middle. Standard deviations go to each side, 7, 4, 1. That would be the normal curve for this particular distribution. And the standard normal curve uses the z-score. The standard normal curve has a mean of 0 and a standard deviation of 1. Right? And the thing you must realize is that the areas remain the same. If you know the area between your specific normal curve for the specific case, the standard normal curve is the same. We haven't changed anything in terms of what the curve looks like. We're just changing the scale on the bottom. So it's almost a trick question. The area between the two z's, the same thing as the area between the two x's.